Okay, we need to go ahead and return to limits briefly here so that we can talk about limits at infinity. Now what we mean by limits at infinity is we're talking about the limit of a function as x approaches plus or minus infinity. Now, but most functions as x approaches plus or minus infinity, they can basically do a couple of things. They can increase without bound, they could decrease without bound, or they could get closer and closer to a particular number. Notice that this function that I've got graphed here, and I didn't list the function, it's really not important what the function is, but this function that I've got graphed here, notice that as x gets larger, notice that this function gets closer and closer and closer to this line. This line, I guess I should label that line. That line is the line y equal 3. So this graph, as x increases, the graph gets closer and closer to y equal 3. And so therefore, you also might remember that would be a horizontal asymptote, which we'll talk about in a minute. Now, for this function, if you look at this function as x approaches negative infinity, in other words, as we go this way, notice that this graph gets closer and closer and closer to the x-axis. And this is the x-axis, which is the line y equals 0. So basically, that's a couple of things that could happen as x approaches infinity or negative infinity. Now, some other things that could happen. Here, notice that for this one, as x approaches infinity, notice the graph doesn't seem to get closer and closer to a number. It just seems to increase without bounds. And then same thing here, except the difference here, whereas this graph is approaching infinity because it's increasing without bound, this function as x gets larger and larger is actually decreasing without bound. So it's actually just getting smaller and smaller. So we would say this limit is actually negative infinity, where over here this limit as x approaches infinity is actually equal infinity. Okay? Now, the definition of limits at infinity are stated like this. It says the limit of f of x as x approaches infinity equals L simply means that for each epsilon greater than 0, there's an m greater than 0, such that the absolute value of f of x minus L is less than epsilon whenever x is greater than m. Okay, I'm just going to summarize that property or that theorem here. Basically, let's say that you choose an epsilon that puts L plus epsilon where this horizontal line is, and L minus epsilon where this horizontal line is. And we know the limit is y equal 3. So let's see what that says. Well, it says that if you were to choose that epsilon, there's some number m, and that number m would be right here, see, because right here is where that graph crosses this and gets inside this epsilon band right here in between these two epsilon, L plus epsilon, L minus epsilon. And it basically just says as long as there's a number m such that when x is greater than m, then the graph always stays within this epsilon band, then you can claim that this line here is actually the limit. And if you want more information, you can research it, but I want to focus more on actually identifying these limits rather than the definition. So now this line y equal L, assuming that limit exists, is actually called a horizontal asymptote. So if the limit of f of x equals L as x approaches infinity or negative infinity, then we get a horizontal asymptote. So if you go back up here and look at this graph, this line y equal 3 is a horizontal asymptote. and over here the x-axis is a horizontal asymptote. Okay, so here's a helpful property. If you have a constant, over x to a power as x goes to infinity, that's always going to be 0. So if you have 10 over x to the fifth as x approaches infinity, that's going to equal 0. If you have minus 2 over x to the 3/4 as x goes to infinity, that's going to equal 0. Now, if x to the power is defined when x is less than 0, then the same is true when x goes to negative infinity. Okay, so here I have 10 over x to the 2/3. Well, x to the 2/3 is defined for negative numbers. So 10 over x to the 2/3 as x goes to negative infinity is 0. But 10 over x to the 3/2 is x to the 3/2 is not defined for negative numbers because that involves a square root. So in other words, the property doesn't apply to this one. But in most cases, you can just say if you have a constant over x to a power as x goes to infinity or negative infinity, you're going to get 0. Okay, now what that leads to these three guidelines for finding limits of rational functions. Okay, so remember, a rational function is a function where the numerator and denominator is polynomials. So let's look at these three guidelines. If the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is 0. So if you look at this rational function, the degree of the numerator is 3, the degree of the denominator is 5, so the limit of this rational function as x goes to infinity or negative infinity is actually 0. The second one says if the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the lead coefficients. Well, here the degree of the numerator is 3, the degree of the denominator is 3, so number 2 does apply. So the limit as x goes to infinity or negative infinity is simply going to be the ratio of your lead coefficients, in this case 12 over 3. So the ratio would be 12 over 3, which is 4. And then if the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function does not exist. So in other words, the limit either goes to infinity or negative infinity. And to figure out which way it goes, we'd have to do more investigation. But here, the degree of the denominator, I'm sorry, I said that wrong. The degree of the numerator is greater than the degree of the denominator, and so therefore this limit does not exist as x goes to infinity or negative infinity. Now, I'll show you the second one. I mean, this can be proved, but it's a little tricky. All right, this represents a polynomial over a polynomial. Okay, so this is just the general ways to write a polynomial. So this polynomial has coefficients involving a's. This polynomial has coefficients involving b's. If you multiply the notice I listed the polynomials with the same degree. Okay, so they both are degree n. So if I were to multiply both of these polynomials by 1 over x to the n, well, what's going to happen is when you multiply the first terms by x to the x to the n's just cancel, and you're just going to get the coefficient of the first polynomial and the coefficient of the second polynomial. Well, then when you multiply these other terms by 1 over n, or 1 over x to the n, well, this n is going to be greater than these other exponents. So actually, you know, this term would be 1 over x in both cases, and the next term would be 1 over x squared in both cases. The next term would be 1 over x cubed in both cases, and so on. Well, what's going to happen? You know that 1 over x goes to 0, 1 over x squared goes to 0, 1 over x cubed goes to 0, and so forth. So when you take the limit as x goes to infinity, all of these terms disappear, and so do all of these terms. They disappear, they go to 0, and so all you have is this ratio of a sub n over b sub n. So that's just the ratio of the lead coefficients. And you could show the other two in a similar fashion. Okay, So a couple more examples. Be careful. Here, the degree of the top is 3, and the degree of the bottom is 3. But be careful. Remember, the lead coefficient is the coefficient of the highest degree term. So the lead coefficient here is not 1, it's -5. And the lead coefficient down here is +3. So the ratio would be -5/3. This one, the degree of the top is larger than the degree of the bottom, so that limit does not exist. And on this one, the degree of the bottom is larger than the degree of the top, so it's 0. So there's a couple more examples. A lot of functions have the same horizontal asymptote as x approaches plus or minus infinity, but there are some functions that can have different asymptotes as x goes to infinity or -infinity. All right, let's take a look at this one. Now, I'll explain it the best I can here for you, but basically what I'm going to do is I'm going to take this and I'm going to divide the top and bottom by the square root of x squared. And so if I divide the top and bottom by square root of x squared, well, the square root of x squared is x, so I'm going to divide the top by x, but since the bottom is a square root, I'm going to use the square root of x squared instead of x for that. Now, when you divide this, you can rewrite this as a single radical here, and then this fraction can be written as 5 minus 1 over x. And then this radical can be written, if you simplify this, you can write that as 3 plus 1 over x squared. Well, this limit is the limit of the top over the limit of the bottom. Well, the limit of the top is just going to be 5 minus 0, because 1 over x is x goes to infinity 0. And this limit of the square root is just going to be the square root of 3 plus 0, because 1 over x squared goes to 0 as x goes to infinity. So basically, you're going to get 5 over square root of 3. And you can rationalize that and get 5 square root of 3 over 3. So that's a horizontal asymptote going one way. Now, what's tricky is when you let x go to -infinity. Because if x is going to -infinity, when you divide by x, you've got to make sure x is a negative value. Well, the square root of x squared can't be negative unless we let have a negative coefficient in front of it. So we're still going to divide x into this just like we did before, but when we divide x into this radical, we're going to use minus the square root of x squared, and because that's going to be the same as x if x is a negative number. Now, but when I divide, I'm going to leave the minus out here, and then I'll divide the square root of x squared into here. So basically, other than the minus that I have, everything else works the same as before. This is going to go to 5 minus 0, and then this square root is going to go to square root of 3 plus 0, but I'm going to have this minus here. So I'm actually going to get 5 over minus square root of 3. So I'm going to have minus 5 square root of 3 over 3 as my horizontal asymptote as x goes to -infinity. So if you look at this graph, you can see that as x goes to infinity, the graph's approaching a horizontal line that's above the x-axis. So that's the horizontal asymptote, positive 5 square root of 3 over 3. But if x goes to -infinity, the graph is approaching a line that's below the x-axis. So that's the horizontal asymptote of minus 5 square root of 3 over 3. So hopefully that helped you understand how a graph can have two different horizontal asymptotes. All right, we'll talk about some other limits involving infinity on the next video.